Good
Good
morning,
morning,
ma'am.
ma'am.
Good morning. How are you all?
Fine, ma'am.
Fine.
So we will begin today with Heisenberg's uncertainty principle. de Broglie's equation तक हम लोगों ने already कर लिया था. आज हम लोग देखेंगे Heisenberg's uncertainty principle.
Yes,
ठीक है? मेरी voice clear आ रही है ना?
yes, ma'am.
Yes, ma'am.
Okay. So we will begin this topic with one video I have just searched from this YouTube. इसको देखो पहले अच्छे से 4 मिनट का वीडियो है हाइजेनबर्ग्स अनसर्टेनिटी प्रिंसिपल पर. Let us try to understand what this concept is. Okay.
The Heisenberg's uncertainty principle, which was given by Werner Heisenberg in 1927. This is the mathematical expression for the Heisenberg's uncertainty principle, which states that the uncertainty in position multiplied by uncertainty in momentum of a microscopic moving particle is always greater than equal to a constant, that is h cross by 2. Now h cross by 2 is also written as h by 4 pi, because h cross, which is also known as Dirac h, where h is Planck's constant, and h cross is equal to h by 2 pi. So the equation can also be written as delta x into delta p is greater than equal to h by 4 pi. This is the famous Heisenberg's uncertainty principle, and it tells a lot about the wave-particle duality of a microscopic moving particle like electron. In this principle, according to this principle, we will understand that if delta x is the uncertainty in measurement of position of a microscopic moving particle like electron, and delta p is the uncertainty in measurement of the momentum, and delta v is the uncertainty in measurement of the velocity, then it is impossible to know exactly where that particle is right now, as well as how fast it is going simultaneously. Stating the Heisenberg's uncertainty principle, we can say that it is impossible to find simultaneously the position and momentum or velocity of a microscopic moving particle like electron with absolute accuracy. So considering this Heisenberg's uncertainty principle, we can see that delta x into delta p is greater than equal to h cross by 2. Or we can say that delta x is inversely proportional to delta p. This means that if uncertainty in position, measurement of position, that means if uncertainty in this means that if uncertainty in measurement of position is small, then delta p will be large. That means it can be predicted with less accuracy. Similarly, if delta x is small, delta p is large. That means more accurately you know the position, less accurately you know the momentum, and vice versa. So this is what is predicted by Heisenberg's uncertainty principle. Apart from this, we have delta x into delta p. In place of delta p, we can write it to be m into delta v, which is greater than equal to h cross by 2. So that means delta x into delta v will be greater than equal to h cross by 2m. And this implies that if the mass of the object is very large, then uncertainty in position and momentum measurement will be quite small. And the smaller the uncertainty is, the more accurately we can measure it. So that means for heavier objects, it is possible to measure the position and momentum while they are moving with absolute accuracy. But for microscopic moving particles with very low mass, say for example the subatomic particles, electrons, protons and neutrons, it is difficult to measure the uncertainty in both the parameters with absolute accuracy. Because of their small mass, the uncertainty would be very large in this case. So these are the two aspects that Heisenberg's uncertainty principle deals with. First is the smaller the uncertainty in position, larger is the uncertainty in momentum. And so both cannot be measured accurately at the same time. Secondly, depending upon the mass of the object, we can measure the uncertainty in position and momentum. That is, if the mass of the object is small, the uncertainty in measurement of position and momentum would be large. So, for massive objects, both can be measured simultaneously. But for lighter objects like microscopic moving particles, subatomic particles, it is difficult to measure both simultaneously because the uncertainty in this case would be very large owing to their small mass. In this, the same thing has been expressed as delta x into delta p is greater than or equal to h cross by 2. If the uncertainty in position is less, then uncertainty in momentum would be high, and vice versa. Delta x would be high when delta p would be low. Take a pause and solve this equation as your assignment. These kind of numericals can be expected in your university examinations, wherein you are asked to find out the uncertainty in one of the parameters. Say, for example, in this question, it is being asked to find out the uncertainty in momentum of the electron which is moving in a region, and the uncertainty in position is 5 into 10 to the power minus 11 meter. Heisenberg uncertainty principle also addresses the question whether we can find electrons in the atomic nucleus or not. For this, let us look at this calculation. We know that electrons cannot be found within the atomic nucleus, and this can be justified by the Heisenberg uncertainty principle. This is the dimension of the atomic nucleus. That is of the order of 10 to the power minus 15 meter. Now, according to Heisenberg's uncertainty principle, we have delta x into delta p is equal to h by 4 pi. Substituting the value of delta p as m delta v, we have delta x into m delta v as equal to h by 4 pi. From there, we can calculate the uncertainty in velocity to be equal to h by 4 pi m delta x. Now, substituting the value of all the constants here, we can have mass of the electron is 9.1 into 10 to the power minus 31 kg. The uncertainty in position has already been specified as the order of dimension of the atomic nucleus, that is 10 to the power minus 15 meter, and value of pi is 3.14. Putting all these values, we get the value for uncertainty in velocity to be equal to 5.77 into 10 to the power 10 meter per second, which is way higher than the velocity of light. Since nothing can exceed the velocity of light, hence we can say that this is not a valid condition. This case is not valid, that electrons cannot be found within the atomic nucleus, because considering this equation, Heisenberg uncertainty principle proves that the possibility of finding the electrons inside an atomic nucleus is nil. So in today's class, with Heisenberg's uncertainty principle, we have come to know that for a microscopic moving particle like electrons, we cannot measure the uncertainty in position and momentum with absolute accuracy. But for massive objects like a cricket ball or a human body or anything which is more massive than a subatomic particle, we can calculate the accurate position, change in position and change in momentum or velocity with absolute accuracy. And this comes from the relation that uncertainty in position and momentum is inversely proportional to the mass of the object. Similarly, we have come to know that the uncertainty in position and momentum are inversely related to each other. So, the smaller the value of delta x, higher is the value for delta p, and vice versa. That means if the uncertainty in position measurements is low, we can measure the uncertainty in position with high accuracy. And if the uncertainty in position momentum is low, then we can measure the uncertainty in position with high accuracy. So this is what the Heisenberg's uncertainty principle deals with, and it expresses the wave particle duality of an electron, which was earlier justified by de Broglie's hypothesis. In our next class, we will study about the Schrodinger's wave equation to explain the quantum mechanical model of an atom. Thank you, everyone.